In this video I'm going to talk about the vector equation of a line. So the vector equation of a line is given here. Okay, so this says that a point on a line with a position vector r can be determined using this equation, where p is the position vector of another point on the line, d is known as a direction vector. Now this is a vector that simply determines what direction the line is pointing in, and t, this is simply a real number. We know the t as being a parameter, so this is actually a parametric equation. So if we show this geometrically speaking, so here we got a line L, and our line is in R3, so we have an x, y and z axis. So we have the point or a position vector of any point on the line, let's call it P, and we have a direction vector, so this gives the direction of a line. I've called this D. So another point on the line, for example P plus D, is given here. This is where our parameter t, if I just go back to the previous slide, if our parameter t here was 1, we just got P plus D, so that's another point, or the position of another point on the line. If our parameter t was 2, we'd have this point, so starting at P, we add on 2 lots of our direction vector D, so this gives us another point on the line. We could also go in the other direction. If our parameter t was -1, remember, multiplying by -1 switch to the direction of our direction vector D, so we have this point down here. So that value of t, changing that value of t gives us a position of any other point on our line. So we're going to look at an example. So we're going to determine the vector equation of a line that passes through these 2 points. Okay, these are position vectors, and we're also going to calculate the position position vector of another 2 points on the line. Okay, so first we need to calculate the direction vector. So all we have to do is subtract these two. Now it doesn't matter what order you subtract them in. So I've taken the second vector and I'm going to subtract the first vector. Okay, so this gives us a direction vector. If we did it in the other way around, all that happened was our direction vector would be negative, whatever these values are. It's still valid, so it doesn't matter which way around you subtract those two. So the vector equation of a line is equal to r equals a plus td. Now this a is any point on the line, so I've chosen a. I could have equally chosen the second vector. Okay, I could have written that second vector there, so that would also give us an equivalent equation of a line. So here we have the first vector plus our parameter t multiplied by our direction vector, and using vector addition we have a single vector which is in terms, or written in terms, of that parameter t. Now by substituting any value of t into this vector, we get the position vector of any other point on that line. So for example, if t is equal to 4, okay, so all I'm doing here is I'm substituting the value of 4 in place of t and evaluating what they are. We have 5, -10 and 3. Now this is the position vector of another point on the line, and if we change t, let's say t is equal to -2, and do exactly the same, and we have this position vector, and this is the position vector of another point on the line. Oops. Okay, with the vector equation of a line, we can do quite a few things, and one of those is determine where lines intersect. So let's say we've got 2 lines, L1 and L2, and these are defined by vector equations R1 equals P1 plus T1 D1. So this is the equation of a line L1. So here we have P1 is a point on the line L1, and D1 is a direction of that line L1, and T1 is the parameter for L1, and similar for R2. Okay, so for the second line we have another point on the second line, which is P2, and we have a direction vector for that second line, D2. Now if we set those two, or the equation of those two lines, equal to each other, if there exist values of T1 and T2 such that the left hand side equals to right hand side, we know that those two lines will intersect. So let's have a look at an example. So here I've got the vector equation of two lines. So I'm going to determine the position vector of the point of intersection. So the first thing I do is I set them equal to each other. So this gives me a system of three equations. We have two unknowns, t1 and t2. Now I'm going to attempt to solve for t1 and t2. So if we subtract the first equation from the third, okay, so if we subtract the first equation from the third, that will eliminate the t2 here, and we're left with 2 plus 3t1 equals 8, and solving that, we see that t1 is equal to 2. If I substitute t1 equals 2 into the first equation, that'll give 1 minus 2 equals negative 3 plus 2t2, which can be solved for t2 is equal to 1. And if we substitute our values of t1 and t2 into the other two equations, we can see that it also holds, so left hand side also holds to the right hand side. So these lines do intersect. So if I substitute t1 is equal to 2 into the vector equation of the first line, so just going to go back a slide. So we saw that t1 is equal to 2, and our equation for the first line was this vector. Okay, so I substitute t1 equals 2, and we get the point or position vector minus 1, 8 and 7. And if I do similar for the second line, so we saw that t2 was equal to 1, and if I substitute that into the vector equation of the second line, I get the same point. Now, because I get the same point, these two lines must intersect at that point. So that's when lines intersect. Another instance we may have is that where we have parallel lines. So if two lines, L1 and L2, are defined by the same vector equations as before, if the direction vectors are scalar multiples of each other, so in other words, let's say d1 is equal to some scalar k multiplied by d2, okay, these lines are considered to be parallel. Okay, so here we have a, geometrically speaking, so here we have L1, so this direction vector is d1, and here we have L2, where the direction vector d2 is some scalar k multiplied by d1. These are parallel lines, and parallel lines will never intersect. So here's an example. I'm going to show that these two lines are parallel. Okay, so what I'm interested in here is their direction vector. Okay, so if we look at the coefficients of the parameter t1, we have negative 1, 3 and 2. So the direction vector of my first line is negative 1, 3 and 2. And doing similar for the second line, we have negative 3, 9 and 6. So that gives me my second direction vector. Okay, well, if we have a look at these two, d2 is 3 multiplied by d1. Okay, so negative 3 is negative 1 times 3, 9 is 3 times 3, and 6 is 2 times 3. So since d1 is a scalar multiple of d2 and vice versa, then these two lines are parallel. If two lines are not parallel and they do not intersect, we say they're skew lines.